Entonces empezamos con el segundo día del Silafae.
¿Qué pasa?
Me han pedido decirle que adentro no está permitido. I'm sorry, I get confused with the languages. So good morning. We start now with the second day of the Silafae. I've been asked to tell you that it's not allowed to carry food and drinks in the auditorium. Okay, so finish your coffee and then. So we are a bit late, but let's start immediately with José Matías-López de la Universidad de Coimbra, dark matter direct detection experiments.
Full screen. No, este no. Este lo quiero cerrar. ¿Vale?
No, hay más.
Así. Mejor, ¿no? Entonces, ya está listo.
Listo, profe, hace para el tinte.
¿Ya funciona? Ya.
Acá, profe, acá adelante.
¿Y la luz? ¿Es del medio?
Sí, no importa. Sí, no importa.
¿Es la luz? Sí.
Sí.
Vale.
Saben de la pantalla.
So good morning. Mejor. So good morning. I'd like to thank the organization for the great opportunity to present our work on the experimental dark matter, so on particularly on WIMP's direct search. So why do we look for dark matter? That is the starting question. Probably the most important cosmological question that we have is the composition of our universe. Many different studies try to answer that question, and we have a budget of energy and mass in the universe. Those are results from Planck from last year. That tell us that the matter that we know, the baryonic matter, is roughly 5% of the total budget, and there is a much larger fraction, totally unknown, that we call, for that reason, dark matter. So if we do the math, this unknown matter accounts for 85% of the matter in the whole universe, and is strikingly unknown so far. And this is extremely important to understand not only the formation of galaxies and the structure of larger structures than galaxies in the universe. So why do we follow this dark matter hypothesis? Well, it's much more than hypothesis. We have many different indirect evidences. I just picked up two of them. The first one is the rotational curves, or the velocity curves in spiral galaxies. Well, that's the case of our galaxy, of the Milky Way. And also, I have here the example of another one, NGC 6503, so I don't know if you can read this. So by Kepler laws, by the amount of mass that we know in the Milky Way, the velocity curves will reach a maximum, then fall down. And what we actually measure is that it basically remains constant after reaching a certain value. Well, that's what we see in all spiral galaxies in the universe. Another piece of evidence is what we get from gravitational lensing. So that means that when we are looking at some particular points in the universe, we see distortions which are much, much larger than what we would expect from the known mass. So that means that there are regions with a much higher concentration of mass than the one we can account for. So what do we know so far about dark matter? Mostly negative information. We know that it's non-baryonic, it carries no electric charge, has no strong self-interaction, and also it's not in the standard model of particle physics. I've picked up this nice graph by Annika Peter, trying to present the possible dark matter particles. In the vertical axis, you may see the interaction strength. On the top we have the neutrino interaction strength, and then it goes down until gravity interaction. And we can see that the highest interaction one option is called WIMP, and it's also called the WIMP miracle, as we can actually test it in detectors. That's why we focus our attention on WIMPs. Supersymmetry theory, as one of the most consensual theories, predicts the existence of these weakly interacting massive particles, or WIMPs, of dark matter. And basically, we know the number. We know that per each of our bodies, about 10 to the 15 of these particles will pass through, and at the best, one of them will interact in a full day. We know also that this interaction rate can be much lower, and even below one single event per ton of target and per year of exposure. So how do we detect WIMPs? We detect WIMPs by their expected elastic scattering of atoms of regular matter. The WIMP wind has an average which is non-relativistic, a little bit above 200 kilometers per second. And the expected energy left by the WIMPs, this blue curve, falls down exponentially. So the rate that we have here, in terms of the energy deposited in the target, goes down with the energy exponentially. That is the main feature we should take off this slide. Also, there is some nuclear form factors affecting this rate, but we'll come to that in the next slide. So the interaction of these WIMPs is usually split into main components. One called spin independent, which means the interaction of the WIMP is done coherently with the full nucleus, and another one, which is the spin dependent, where the spin carried by the WIMP will interact with the total angular momentum of the nucleus that it will interact with. Most of the time, the focus is on the first one, on the spin independent. As for larger atomic masses, so above 30, it dominates the two components. As you can see, the cross-section is proportional to the atomic mass squared, and also to these nuclear form factors. So this means that the expected rate of events depends on the target we are using. I've just plotted three of them here. So the green one is argon. I don't know if you can see it in the back. The green one is argon, the next one is germanium, and the top one, the blue one, is xenon. So in this, we are going up in A, of course, and as you can see, from argon to xenon, we have much more than 1 order of magnitude separating the two curves at the lowest energies. The form factor affects mostly the higher A nucleus and the higher energy deposited. So that's why you see this blue curve suppressed faster at higher energies than the germanium and the argon ones. So the WIMP direct detection, we can summarize the challenges that we face when we try to measure it in detectors. The first one is, of course, we are dealing with very low energy levels. As you can see, again, from the curves here, this is exponentially going down. This is an exponential scale. Okay, we are back. So I was telling you that we have a log scale here. Those are exponential, falling exponentially detection rates. So this means we expect to see most of our events below basically 50 keV. So we are dealing with very small deposited energies. We want our energy thresholds in the detectors to be as low as possible. In practice, this means a few keV to get the most of this area here in the total detected rate. The event rates are, of course, extremely small, and that means we have to be able to discriminate the background as well as possible, and also to lower this background to an ultra-low level. That means we really need to understand very well the sources of our background. And finally, we will need large detector masses as the detection rate is proportional to the number of atoms we have in the target. So we will focus, of course, in these two points out of the four, as 1 and 4 are straightforward. So how do we discriminate background? Most of the background interacts at the atomic level, and it's mostly from gamma and beta origin, and we call it electron recoils as the interaction occurs at the level of the atom, of the electrons in the atom. In opposition to the WIMPs that we expect to interact at the nucleus level, so this means a different channel, and with two different channels, we will have a way to differentiate what our events from the background. So comparing the signals you get from the two channels, either comparing charge with prompt light or even heat, we can separate the two kind of events, the two channels, and have there a very powerful discrimination tool. Additionally to that, and this is an example of Xenon 100 detector, one of the experimental efforts going on. This is a cut of the detector. So this will be the axis of the detector, and up here the boundaries of the detector volume, up here, and here the outer walls. So if all these points are background, and if we use some of the outer thickness of the target just as a shield, then we can, of course, do self-shielding. That's what we name self-shielding. And, of course, we cut to a fiducial volume inside the target where we we leave out most of the background. So both by self-shielding and knowing the position of our events, we can do this fiducialization and further improve the background discrimination. Of course, this is not enough. And after discrimination, we need to look at the backgrounds. So we already have seen that gamma and beta act at the atomic level and through this electronic recoil channel. And to reduce the level of this gamma and beta external background, we have to shield our detector, our target. But also, the material that composes the detector and the target itself contains radioactivity, so we have to be extremely careful in selecting the material that we will use for our detector. As for the nuclear recoil channel, not only WIMPs but also neutrons will interact this way. So this means that we really have to be careful with neutrons, as those will not be distinguishable from the WIMP signal. Their origin is from, it's twofold, is from muon induced reactions in the rocks and in the atmosphere, or it comes from the rock itself. So that means that if we want to lower the flux of muons, we have to go underground, to underground labs. And in those underground labs, also in the rocks, we have creation of neutrons. So we have to use shields to reduce that component. So going underground and reducing the muon level, we have plenty options at the moment, and some new ones just around the corner. Just for instance, if we take this middle scale one, the Gran Sasso in Italy, we have a reduction on about 6 orders of magnitude on the muon flux. So it comes down after this is below about 1.3 kilometers of rock and the Gran Sasso mountain, and this is equivalent to 3.6 kilometers in water equivalent distance. So this is already enough in terms of reduction of muons. In terms of shielding the detector, we have here, this is the aspect of one of the detectors, the Xenon 100 detector again. Then it's inside this cryostat, and you can see here, this is the shield used in this case, which has 4 layers. 2 of them, in this case, are low Z, so this is plastic. Outside there is water to moderate the neutrons. And then we have high Z. There is some lead, about 20 centimeters of lead here, and then a layer of copper to reduce the gamma events. At the moment, these shields are being, these solid shields are being totally put aside and changed by large water shields that will also act as muon veto. So let's talk about the material selection in these detectors. Again, this is the Xenon 100 detector. We have here one of the PMT arrays, the second PMT arrays, and those PMTs are Hamamatsu made. They have been developed together with the Xenon collaboration, and they have been carefully selected in terms of materials to reduce their background by about 50-fold. Even though they are still, as you can see here in this pie chart, they are still contributing about half of the background created by the detector components itself. Also, their driving bases, their electronic bases, have a large fraction of, contribute to a large fraction of the background from the detector itself. We have to account that even the target, this kind of purple, not cyan pie slice, is the liquid xenon itself, which is the target. And as always, we do not have pure noble gases. We have also traces from other gases like krypton and argon, which have radioactive isotopes. And then we have radioactivity from the target itself. This plot here is what we get after selecting very carefully all the materials. Even the smallest screw is screened and chosen to be the most radio clean possible. And this is what we get after that. So I don't know if you can see the black. There is a black curve here, then a red one. So the black one is the data on the background. The red one is the Monte Carlo, and they fit extremely well. So it means that we understand the sources of our background. The external background is still the largest fraction, so it's the gray curve here. And as I was just talking, the traces of krypton and argon are also important. Krypton is here at this blue curve that you see here. It's the krypton contamination component, and also the radon that is present in the air of the lab. Those also add some component of background, not so significant in this case, this green one. Well, the fact is that we only are looking at the lowest energy section of this graph, just below 100 keV. So let's have a quick look at the different WIMP direct detection experiments we have at the moment. Just to keep in mind that we either look at a single signal, like looking at heat, like this Cuore, Coupe, Picasso, Simple, Pico do, or only charge, only light, or a combination of two of these. For instance, CDMS looks at both heat and charge, and Edelweiss as well, and charge and light is used by dark side, the argon, dark matter, Panda X. So there is all these different approaches in terms of getting the information from one or two sources, and we'll see in a moment that there are even more different approaches on other aspects. The interesting factor is that although most of these efforts try to look for WIMPs, they are also sensitive to other dark matter candidates, like axions and axion-like particles. We can see here two graphs, one for solar axions, the other one for galactic axion-like particles. Not only their origin is different, but the mass scale is different for both. One goes from the micro EV up to about 1 keV over c squared. The other one goes beyond that, from 1 to a few dozen of keV. The axions are expected to interact in the same way as photons with these targets. So we expect to have an axioelectric effect. And what you see in these curves, and in the next ones we will see, are called exclusion limit curves. That means how sensitive are the detectors once you cannot see an event. And when we draw one of these lines, like this red line here from Edelweiss, it means that we have excluded everything above the curve. So at the moment, solar axions are excluded in this parameter space above 8 10 to minus 12 in this parameter that's connected with the axioelectric effect. And when we look at galactic axion-like particles, the limit is not constant, but it's at the level of 10 to the minus 12 as well. The present scenario, in terms of sensitivity of the different efforts on detecting WIMPs, has to be accounted in terms of if we are looking at the spin-independent or spin-dependent interaction components. I'm starting by the spin-dependent one, which is usually less stringent than the main component. This spin-dependent is seen in terms of either proton interactions or neutron interactions, so it's split into two components. If we look at the WIMP proton interaction curves, we see that we are at the level of 10 to the minus 39 scale in terms of interaction, cross-section interaction in square centimeters. Here, the lower atomic mass targets have advantage, like the case of SIMPLE, which uses fluoride 19 or COOP. On the WIMP neutron interaction cross-section, we are also at the same level. We are in the 10 to the minus 40 square centimeter scale, exclusion limits. It's this blue curve set by Xenon 100. So it's interesting to see that heavy targets, high atomic mass targets are very sensitive here as well. And let's see the spin-independent exclusion limits. So this one is much more stringent. So remember, we're on about 10 to the minus 40 on the spin-dependent scales. Now we are down almost 6 orders of magnitude. So in spin independent, we have this special kind of shape. Remember that we are looking in the x-axis at the WIMP mass from about 1 to above the TeV. So we see that most of these experiments are sensitive, but only starting in a few JeV. So there is some parameter space which is not being covered in the left-hand side. And then we are much more sensitive from above 10 JeV up to the end of the scale. As you can see, there is a strong exclusion. This parameter space in the 10 JeV, 20 JeV is extremely constrained by many different experiments, and there are some anomalies there. Some experiments do see some modulation, like Dama Libra or CDMS, Silicon, Cogent, Crest. Well, at some point they have seen these annual modulations, which of course are extremely nice to see, as you would expect to have a dark matter signal with that kind of modulation. The Dama Libra, for instance, is collecting for more than 10 years now and has this modulation above 9 sigma confidence level. But we'll see in a moment that this is not very well understood. For instance, the CDMS silicon detectors in the last results have seen 3 events in the dark matter region. And again, those could not be claimed, we'll see in a while. Crest had a similar effect, but they have more recent results, and they could not confirm that kind of modulation, so they have to retract their results. But let's look in particular to one of them. So some people are using this funny name, thresholdinos, to this dark matter signal that cannot be understood. And we have, of course, to be aware that we are looking at the lowest energy beams of our histogram, right? So, unfortunately, that's where we have the systematics appearing as well. And as we, in spirit, attribute to Rutherford, he said, we should be ready to be skeptical of the results from your uppermost and lowermost beams of your histogram. And sure we do. Coming back to this highly constrained region in around the 10 JeV, we have dozens of results here from CDMS, Lux is the last one, CDEX as well. Well, it's heavily constrained, and at the same time we have those anomalies. For instance, the results from CDMS silicon, which is our silicon crystals, so it's a semiconductor target, roughly about a kilogram of silicon crystals. We have observed 3 events. But these events are not matching the known background, so the model of background that this experiment had constructed. And the likelihood analysis shows only less than 1% probability for these events to be background. So is this dark matter? Well, unfortunately not, as we know. We can fit these results to about dark matter of about 8.6 JeV and to this cross-section about 10 to the minus 41. And then let's see how it looks like in more sensitive detectors like Xenon 100 and Lux. So these events with this mass and with this cross-section will give in Xenon 100 a signal of about 220 events, or more than 1,500 events in Lux. So basically this excludes those results from being any kind of dark matter. And now the famous gamma modulation. So this curve here has a blue curve which is attributed to muons, then has the dark matter signal, which is this dotted black curve, and then this green one, which seems to follow very closely the dark matter curve. So Jonathan Davis, last August, presented in PRL one possible explanation for this, which would be that the modulation seen in gamma would come from a combination of neutrinos and muons, not muons exactly, but neutrons induced by this muon in the atmosphere. Well, the fact is, although this being published in PRL and being mathematically correct, both Cogent and the DAM itself published about a week later very strong arguments showing that this could not be true. For this to happen, the neutron fluxes will need to be about 4 or 5 orders of magnitude larger than what we actually have in the gamma detector. So again, we do not know what is this modulation, what's the origin of this modulation. So the fact is, there is plenty work ahead, and we need all kinds of efforts to combine if we want to constrain and discover WIMPs. This world map has, not all of course, but most of the current efforts. As you can see, we have a few in Snow Lab and other labs in North America. We have a collection of them in Italy and Gran Sasso, and then in France, and in other places in Europe, and also in the Far East. And and recently we have one in the South Pole. Now I will try to review the different approaches that we have in terms of targets, in terms of techniques, on all these efforts. So the first one is the experiments that work at the millikelvin range, so very low temperatures. They have very high sensitivity to the WIMP channel, as they can present also very low energy thresholds below the keV. They are very sensitive to the low mass WIMPs. So when we say low mass, we are aiming at less than 10 GeV. They rely on two different information channels. They try to look at light and phonon or heat, and charge and heat. And this is an example of the two bands. This is the background or electronic recoil region, and down here the WIMP channel. The most recent data from this kind of events comes from Super CDMS, CREST, and Edelweiss. As you can see, all of them use basically, the first one uses germanium and silicon, and the next one uses, CREST uses cadmium, tungstenate, and then germanium in the case of Edelweiss. Super CDMS just released new results a few months ago, and is proposing to have a larger detector at SNOLAB as well, with up to 92 kilograms of germanium and 11 of silicon, and then a smaller, that they call light, a smaller parallel experiment as well. CREST started a run this year, released some results, and is taking more data with their brand new 18 detectors that add up to about 5 kilograms in Gran Sasso, Italy. And finally, Edelweiss has about 30 kilograms of target and started with these new detectors in June of this year. By the end of this year, they expect to reach about 300 kilogram days of exposure, and in 2016 to go up to 1.2 tons, which is already a very large number. In the future of this type of approach, we have Super CDMS at SNOLAB, which also plans to collaborate with Eureka and have a multi-target. And this multi-target will have the germanium and again the calcium tungstenate, and start taking data in 4 years from now. And they want to reach for 10 to the minus 47. So the this is again the curve that we saw a while ago with this bound here, the neutrino bound, which is basically the physical limit to detect WIMPs. And this new future cryogenic aim to go down here in this above 10 GeV region, but it will be mostly sensitive in the lower mass region. That's where they will make a great improvement. A new approach, different approach that DAMIC is following is using CCDs to detect low mass WIMPs. So CCDs allow to distinguish the different type of events, the background events from these events, through their path in the CCDs. The detector is not very large, it's only 100 grams, the one that is in construction at SNOLAB, and the results are expected next year. The results that have been released so far are only less than 0.1 kilogram days, so it's a very small exposure. But again, it's an interesting way of, and a different approach that could add some information to the process. We also have bubble chambers. Bubble chambers are a very simple kind of detector, very cost effective. Basically, as the nuclear recoils will have very short ranges, as the DEDX is the stopping power is very high, it will create bubbles that will be detected by different means, acoustic, visual, or even motion detectors. And they have very large rejection factors for minimum ionizing particles. So some of them are simple COOP, Picasso, and Pico 2L, which is the first collaboration between Picasso and COOP. In the future, Pico will construct a larger detector, 250 liters, of C3F8 with a nice 3 keV threshold. So here we have some images of COOP, of the COOP CF3 iodine installation at Snow Lab that had a physics run until May this year. This is Picasso at Snow Lab, and again, here is Pico 2L, 2 liters. So finally, we have the novel liquid detector concepts, which have 2 branches. So either we have single phase liquid, or we have double phase, the time projection chambers, where we have a liquid target and then some gas on top. These approaches use the first pulse of light. So in the case of the single phase, the WIMP will interact here and will create a light pulse, a prompt light pulse, that together with pulse shape discrimination will allow us to discriminate from background. This is particularly effective when we are using argon as a target, as the target response is delayed in time and is then very much fitted to this pulse shape discrimination. The TPC approach, well, this one relies on the fact of having also the first pulse, the first prompt light, and then as some charge is created as well with the first light, it is drifted upwards, and then getting up here, it will give proportional light, so a second signal of light. With the 2 light signals, S1 and S2, we'll be able to discriminate from background. This is just an example of how it looks like in a Xenon 100 detector. This is a 9 keV WIMP-like event. The first signal, S1, is seen by the lower PMT array, and it's very hard to see, but this is about 100 photons divided by these about 80 PMTs. So that means, in average, each PMT reads 1 or 2 photons at most. The top PMT array will collect the light from the second pulse. It's quite localized, as the charge signal is basically within 1 or 2 millimeters. And we have not 100 photons, but now here we have an amplified signal, about 3,000 photons for this energy. And basically, it's distributed in less than 10 PMTs, so it's very localized. From the time that goes from 1 to the second, we will know the depth of interaction of this event, and of course, from the localization of this S2, we'll have the X and Y position. So that's how we reconstruct the position of the event. The recent data from these noble liquid detectors, we will start talking about the single phase ones. We have 3 ongoing. So we have XMAS at Kamioka, which is a xenon target, and the argon targets of Deep and Clean that are operating at Snow Lab. So XMAS has a little bit less than 1 ton of liquid xenon, and only about 100 kilograms are fiducial. And they are, at the moment, they are taking data after being stopped for 2 years with a background problem. clean has about 500 kilograms of liquid argon and about the same fiducial mass as X mass, and is expected to run later this year. Deep at Snow Lab is a larger detector. Is not only the total mass is a few times larger than clean, but the fiducial volume, so the effective target, will be about 1 ton, and at the moment is taking data, and we expect to see the results still this year. And finally, the TPCs. So at the moment, we have 5 TPC detectors running in the world. We have Xenon 100 in Gran Sasso. We have Lux at Surf. In the Jinping Chinese laboratory, we have Panda X. In Canfranc, argon dark matter, and also in Gran Sasso, we have dark side. So the first 3 of them are xenon filled, and xenon has been running for 6 years now. Lux is twice as much the size. Panda X, a little bit smaller. On the argon ones, only dark side has been running so far, and they made just release some data, and they plan to run with depleted in argon 39 in a few months from now. Argon dark matter is commissioning and expected to run later this year. So this is just an example of the Lux dark matter data. Of course, no event, and this is so far the most stringent curve, reaching the 10 to the minus 46 square centimeter scale. The next generation of liquid xenon detectors, only one is being constructed at the moment, Xenon 1 ton in Gran Sasso, with about 3.3 tons. In the future, this detector will be upgraded to 7 tons. Lux will come up with the same size of detector, and X-Mass wants to go up to 5 tons. There is a design and R&D study which tries to look at larger detectors, the feasibility of having 20 tons of liquid xenon or 50 tons of liquid argon. Let's focus on the one that is being built, the Xenon 1 ton experiment. It's being constructed since a year from now, and we expect it to be commissioned in mid-2015 and start the dark matter run in a year from now. And the goal is to go down to 2 to 10 times to the minus 47 square centimeters. Most of it is completed. Only the TPC is under prototyping. I had here a video, but I think I don't have time to show you this video. 3 minutes for the video. Can we show the video? Okay, so let's move on then. So after Xenon 1 ton, which is currently built, we will have in 2 years of measurements, and in 2018 a very fast upgrade. We'll only change the TPC inside this cryostat and make a larger detector to hold 7 tons. So a very simple change, only more liquid xenon, more PMTs, and some electronics. So Darwin is a very comprehensive group of people, so it is at the moment 26 groups gathering most of the community in the US and Europe, trying to look at the ultimate detector. And there are two different approaches. One is to look at a single detector with argon, 50 tons of argon, or 2 detectors in 2 different water shields, one with xenon, another one with argon. So the expectation is above 10 JeV to go down and explore almost all parameter space. That is what's expected from this study. And okay, once we see a signal that we can claim it's dark matter, how well can we reconstruct the mass and the cross-section of this detector? Well, basically, there is this study by Newstead that he made a Monte Carlo simulation with a cross-section of 3 × 10⁻⁴ using 3 different exposures: 10 ton years of xenon, or the double, or even adding 10 ton years of xenon with 20 ton years of argon. So those are the colors that you see here that are plotted here. He made the study for 20 GeV, 100, and 500, and what he found out is that mostly we can reduce uncertainties in mass, but not in cross-section. Using the best of them, so the blue one, and going down in cross-section, so not only the 3 × 10⁻⁴, but going down 2 orders of magnitude, we see that uncertainties get larger and larger, and of course we cannot overcome the astrophysical uncertainties that are the main reason for this. Again, and we have directional information as well. This means if we study, if we use detectors that brings us direction information, like this study here shows, we'll have an improvement, and probably we can go beyond the neutrino bound, as we have different peaks in the WIMP and the neutrino parameter of interaction. So going very fast here, on directional detectors, they are in R&D at the moment. We have Drift, the MT-Picino at MIT, we have MIMAC at Modane, and New Age at Kamioka, all of them using low pressure gas to look at the direction of dark matter. This, I'll pass over this as we have reached the end of time. This is the irreducible neutrino background, and basically to show you that some neutrinos can be suppressed as they interact at the electronic recoil level, but some not. So basically we are limited by the neutrinos in 10⁻⁴ below 6 GeV of mass. And this last slide is to show you that, again, the neutrino bound is not universal. So it depends on the target that you are using. For instance, here, a single element target, we show differences here on the change from this lower mass to the high mass. So in the intermediate region, there are some quite significant difference if you go from xenon to germanium, argon, or silicon. In the compound targets, there are also some differences, but when we take into account the energy, they are not so significant. And this is on the spin dependent. Again, if we use that neutron-only interaction, the single element will have the lowest neutrino bounds. But if we look at the proton-only interaction, we'll have to go to the compound targets to have lower neutrino bounds. And finally, when do we expect to detect dark matter? We are going down at a pace of reducing the exclusion limits at a factor of 10 every 3 years. So Darwin is expected to work in 2026. Maybe then we will see some dark matter and understand its nature. Thank you.
Thank you for the nice talk. I'm sorry to speed you up, but we started already a few minutes late. So are there questions or comments? Yes.
First, thank you for this very nice tour of the area. You explained very well the discrimination against gammas and electrons, but I failed to understand if there were any news about the discrimination of neutrons. They are not as abundant, but they are these are tricky backgrounds, no?
Well, we cannot discriminate neutrons. We can only suppress the neutron level, but not discriminate.
Yeah,
At the moment, maybe in the future, with these directional detectors, we'll be able to separate the two. But I don't think so.
I mean, I have in mind the argument of the COPE detector, where they say that, for example, in the case of a neutron, you have multi-scattering,
Yes.
contrary to the WIMP, which will have only one scatterer in the volume.
Well,
Yeah,
sure. That depends, of course, on the geometry and the size of your target. If your size is strong enough to have a multi-scattering of neutrons, of course, sure, you can do that kind of background reduction in neutrons. But so far, up to the level we have right now, which is below the ton level, that is not the case. But maybe in the future. Thank you.
thanks.
One other question?
I think I know the answer to this, but still I'm interested in your comments. Would you comment on this essentially recent argument that we might live in this pocket where even though our galaxy is dominated by dark matter, we here in the solar system might not have very large density of dark matter, and how does that affect to this direct
I'm not sure if I
experiment?
understand your question.
So there were some argument a few months ago, or probably a year or 2 years ago, by some, I think it was some people from Chile actually, some astrophysicists who claimed that based on the dynamics of the galaxy, we might live in a pocket where there is no dark matter in our solar system. I'm not sure if you're aware of this. So.
Well, yes, there are plenty different opinions on something that we have never seen, right? So we can only say that we are looking for it on Earth, and we expect to see it. That's all I can tell.
Yes, I don't get fully the point why you roll out DEMA data, because seems there is an explanation that is able to reproduce the time period. But as I understood from your words, the order of magnitude of the amplitude is four times for order of magnitude far from the data.
Yes.
And so this means it's not an explanation.
There is no explanation that, let's say, physically sound explanation, no.
Okay. So it's not ruled out.
It's not ruled out. We just don't know how to explain it.
So one last question is there.
It's just a technical question. When you show to us that the next step of the detector is to increase in size of the target, but the shield will be the same, what is the impact on the background of...
Thank you very much for that question. That was something I should have bring up in the presentation, and I just forgot about it. Much more important than making these detectors larger, we need to, if we want to increase the sensitivity, we need to lower the background first and then only think about going bigger. If we just think we can do it bigger and that's enough, nonsense. Usually if you do it bigger, the background scales up too, and you end up with a less sensitive detector. So the largest challenge in all these detectors is to lower background, and that's of course non-trivial.
Okay, let us thank now the speaker again. And we now proceed with Alejandro Ibarra and the theory of dark matter.
Piso. So thank you very much for the invitation to come to Medellín. And so I was in charge of reviewing the theory of dark matters. Of course, it's going to be quite challenging, so I will focus only on a few aspects. And yes, discussing the previous presentation, there is now evidence for particle dark matter in a wide range of distance scales. So at the moment, there is no evidence at the scale of the solar system, but we have evidence at the scales of galaxies, both at the size of the largest galaxies, like M87, with a size of several hundreds of kiloparsec, and also at the size of the smallest galaxies, such as Sewe-1, that has a size of a few hundred of parsec, and that was discovered quite recently, only 8 years ago, by the Sloan Digital Sky surveys. There is also evidence of dark matter at the scales of classes of galaxies, as indicated in this image of Abel 1689. So this is the optical image of this cluster of galaxies, and this is the corresponding dark matter image. So this is the matter that is necessary in this cluster to produce the lensing images that appear here and there. So it is necessary to introduce this new component of matter to explain this image. And finally, there is also evidence of dark matter at the scale of the whole universe, to the extent that now we know that approximately 27% of the energy content of the universe is in the form of cold dark matter. Okay. So there is no doubt that the discovery of dark matter was one among the many great discoveries of physics in the 20th century, and it's also amusing to think that it was one of the first particles to be discovered. So the first particle to be discovered was the electron in 1897, the next the proton, then the next one was the neutron in 1932. So of course you can think that the neutron was theorized by Pauli in the 1930. The next one was the positron by Anderson in 1932. And the first evidence of dark matter was presented by Fritz Zwicky in 1933. So it was one of the first particles to be discovered, and despite it was discovered so early, we know actually very little about this particle. So when a particle physicist wants to know something about one particle, one goes to the particle data group booklet. So for example, here we have all the properties of the pion that was discovered much later than the matter particles. So here it is the mass, lifetime, decay modes, branching fractions, etc. But the corresponding page for the matter particle does not even exist, because we practically know nothing about this particle. We don't know the spin, we don't know if it is a scalar, a fermion, a vector. We don't know the mass. We don't know if it is completely stable or whether it decays with our lifetime. If it decays, we don't know which are the corresponding branching fractions, and so on. So if the 20th century was the century of the discovery of the matter particle, we hope that the 21st century will be the century where we'll be able to identify the properties of the matter particle. This is not going to be easy because the parameter space of the matter particles is huge from the point of view of theory. So this is this parameter space presented in cross-section with protons and the matter mass. So you can see that here the matter mass ranges over almost 35, 40 orders of magnitude. And for the case of the cross-section with protons, it ranges over almost 50, 40 orders of magnitude. So of course, it is impossible to devise an experiment that can probe all these matter particles all at once. And also, it is impossible to make a presentation that will cover all these matter particles. So in this talk, I'm going to concentrate on a few matter candidates. So first, I'm going to concentrate on the stellar neutrino that has received some attention in the last year. So stellar neutrinos is a very appealing dark matter candidate. It just consists on adding to the standard model particle content one new particle, which is this sterile neutrino. There is no new symmetry invoked. And then this model, in the simplest version, only has two parameters, which is the dark matter mass, or the stellar neutrino mass, and then the mixing angle of the stellar neutrino with the active neutrinos. So here the theory and the phenomenology is quite rich, but there are 5 things that you should know about the stellar neutrino dark matter. First, that stellar neutrinos are produced in the universe via this mixing between active and stellar neutrinos. So it is basically an oscillation process. Secondly, the stellar neutrinos should not be overproduced, and then this requirement gives us an upper limit on this mixing angle as a function of the dark matter mass. Next, if there is a lepton asymmetry in the universe, this can resonantly enhance the dark matter production. This is very similar to MSW mechanism inside the sun, and therefore it is possible to produce the same amount of dark matter with a smaller mixing angle. Fourth, stellar neutrinos are, of course, fermions, and they obey the exclusion principle, and this means that it is not possible to have an arbitrarily large number density of dark matter particles in a given region of space. So in particular, in dwarf galaxies, we know what is how much matter is there in the dwarf galaxy. We know what is the size of the dwarf galaxy, And since we cannot pack an infinite number of fermions in this space, this gives us a lower limit on the dark matter mass. And finally, stellar neutrinos are not absolutely stable, but they decay into an active neutrino antiphoton via this two-week process. So with these 5 things in mind, one can construct the parameter space, the parameter space of the model. So this is the mixing angle. This is the mass. So here in white is the allowed parameter space. And then here you can see the different constraints that I was listing before. So this is the line corresponding to overproduction, assuming that there is no lepton asymmetry. This is the simplest minimal model. Then if you have a lepton asymmetry here in units of 10 to the minus 6, so this corresponds to 25 times to the minus 6 for the lepton asymmetry. Here one can rationally enhance the production of dark matter particles, and one can produce the correct relic abundance with a small mixing angle compared to the case when there is no lepton asymmetry. Then the phase space density considerations gives us a lower limit on the fermion dark matter mass, which is about 1 keV. And then finally, the dark matter decay produces X-rays in this mass range of a few or tens of keV, and this is the corresponding limit from the non-observation of an X-ray line in the sky. Okay? So you know this is the parameter space which is allowed by this model. So you can see that if we have X-ray observations which are more and more precise, we can start sweeping this parameter space and eventually closing the whole parameter space. So this improvement in X-rays has been happening over the last 10, 20, 30 years, and there was quite some excitement early this year when there was a recent hint for an unidentified X-ray line signal. So this is the spectrum of a stacked analysis of different galaxy clusters, and this is the spectrum coming from M39, and then here in this spectra, I don't know if you can see it, here you can see the different data points, and then here you can see the predictions from the theory. And then here there's an unidentified X-ray line that is a bit difficult to see in this plot, so to help you to find it, this is the corresponding excess. And again, here it is difficult to see it, so to see it better, it is much easier to show the residuals compared to the expectations from power loss. And here you can see this excess at 3.5 keV that amounts to about 3 sigma, a little bit more than 3 sigma. Okay. So there were several tests that were done by these authors, by Boyarsky and Bulbul, to the existence of this line. So first of all, this line was not observed in a deep blank sky. So instead of looking at cluster of galaxies or M31, you look at a random part of the sky. And then in this part of the sky, this blank sky data set, no X-ray line was observed. So this means that this line is probably not of instrumental origin. Also interesting that this line was observed in M31 and was observed in the Perseus cluster, and they were not observed at the same energy, but the difference in energy could be explained by different redshift of these two objects. So it was observed in these different data samples at the corresponding redshift. Also, these authors, they were making a careful study about the possible atomic origin of this line. They could not identify a clear atomic origin, and therefore, they speculated that this line could be originated by stellar neutrino decay. And this assumption, this is the corresponding parameters that were derived by these two authors. So you see that the parameters are consistent, and they correspond to this parameter space, to this region of the parameter space, which is allowed by all these different considerations from dark matter production and from phase space density. Okay? So it's quite exciting because it seems to be consistent with everything that we know about the stellar neutrinos. Perhaps the only caveat is that in order to produce this dark matter particle, it is necessary a lepton asymmetry in the universe which is of the order of 10 to the minus 5, which is much, much bigger than the corresponding, or that the baryon asymmetry that we know exists in nature. Okay? So in principle, it's not a problem. Actually, people have devised mechanisms to generate such a large lepton asymmetry without generating at the same time a large baryon asymmetry. Also, it could happen that mechanisms could be at work. So of course, this corresponds to the simplest thermal production, but stellar neutrinos could be produced non-thermally. Or also it could happen that the decay